Hello and welcome to lesson 10 of module 1. Today we're going to be doing all operations in scientific notation, adding, subtracting, multiplying, and dividing when given word problems. So today the first step is going to be identifying, well, which one do we need to perform, and then the second thing is going to be actually performing that operation and solving our question. Let's go ahead and get started. Alright, beginning with example 1, it says the world population is about 7 billion. There are 4.6 times 10 to the 7th ants for every human on the planet. About how many ants are there in the world? Okay. So what we're going to first do is identify what operation do they want us to do here. Do they want us to add these numbers, subtract them, multiply them, or divide them? So it's saying that there are 7 billion people. For every one of those, there's this many ants. So we're timesing this number by this number because for each one person, there's this many times ants. Okay? First thing we need to do after that is write this number in scientific notation. Now, 7 billion is 7, and then we have our millions, and then we have our thousands, and then we have our ones. So that is 7 billion written out. We're just going to turn that into scientific notation. This is having 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces to get the decimal right here to our leading digit. So this is going to be 7 times 10 to the 9th. Okay? And this number is already written in scientific notation, and we're just going to be multiplying those two numbers together. Now we have 4.6 times 10 to the 7th. Okay? Just to review, what we do when we multiply numbers that are written in scientific notation together is we multiply our numbers, okay? And then we add our exponents. And we keep it in scientific notation if we need to. So 7 times 4.6, if you do that in your calculator, you're going to get 32.2. And then we're keeping times 10. And we have 9 plus 7. This is to the 16th power. Okay. The last step here is to check and make sure that this is written correctly in scientific notation. It is not. Our leading digit is 32. We need it to be one space over. So we're going to make this one space smaller. Okay, so we made that number one space smaller. So we make this number one bigger. 10 to the 17th. All right? And then because this is a word problem, we want to answer our word problem in a sentence about how many ants are there in the world. There are about 3.22 times 10 to the 17th ants in the world. That is our answer. Make sure you have it down before you move on to the next slide. All right, example number 2. A certain social media company processes about 990 billion likes for every year. If the company has approximately 8.9 times 10 to the 8 users, about how many likes is each user responsible for? Okay, for each year. So we have all of these likes, a bunch of likes, and it's all these people that are doing these likes, right? We want to figure out how many likes each person does per year if it was split like evenly. So the key word there is split up between all these people. When you split something, you're going to divide. So that's the first thing we needed to identify. What operation are we doing? We're going to divide. So we're starting with 990 billion. Let's go ahead and write that number out and then write it in scientific notation. 990 in our billions. Nothing in our millions, nothing in our thousands, nothing in our ones. Okay? And the next thing I'm going to do is write this number in scientific notation. It's the same as 9.0 or 9. And we're moving our decimal point 3 6, 9, 10, 11. 11 spaces to get to this. Oh, it's actually 9.90, sorry. Or 9.9. So get to our leading digit, which is 9.9. We move 11 spaces. Okay. So we're taking this number, 9.9 times 10 to the 11th, and we are dividing by this number, 8.9 times 10 to the 8th. So our division problem is 9.9 times 10 to the 11th divided by 8.9 times 10 to the 8th. Okay? When we divide numbers in scientific notation, we divide our decimals or our numbers like regular, and then we're going to subtract our exponents. Looking at this, 9.9 divided by 8.9 comes out to 1.11235 ... I'm just going to round it to 1.1. And 11 take away 8. 11 minus 8 is 3. Okay. So this comes out to 1.1 times 10 to the third. This is not a very big exponent. We can actually write this number out as what it actually is. So if this is written in expanded form, which means we just want to write it as our actual number, not in scientific notation, we're just going to be moving this decimal point 3 spaces, okay, to make it 3 spaces bigger. So this is actually 1, so we move around that 1, 2, 3, 1, 2, 3, 1100. So each person is responsible for 1100 likes per year. And that is our answer to this question. All right. Make sure you have it down before you move forward. All right, here is our third example. I don't know why there's no 3 there. It says, in 2010, Americans generated 2.5 times 10 to the 8th tons of garbage. There are about 2,000 landfills in the United States. Assuming that each landfill is the same size and the trash is divided equally among them, determine how many tons of garbage were sent to each landfill in 2010. So first we need to identify what operation do they want us to do. I highlighted a really important piece, divided equally. We are going to be dividing here. We're trying to figure out how is this garbage split up between all these 2,000 landfills. Okay? So the first thing we want to do is write this 2,000 in scientific notation. This would just be 2 times 10 to the 1, 2, 3, third. Okay? And from there we can write our division problem. We have this much garbage and we're splitting it up to this many landfills. So 2.5 times 10 to the 8th is being split up into 2 times 10 to the third landfills. All right. When we divide, we take our numbers and we divide them like regular. 2.5 divided by 2 is 1.25. And when we divide with our exponents, we subtract. 8 take away 3 is 5. We want to check and make sure that this is in the correct representation of scientific notation. It is 1.25 times 10 to the 5th power. Our leading digit is less than 10, greater than 1. If we wanted to write this out, just to show you what this would be written out, it would be 1, and then we're going to move that decimal 5 spaces. 1, 2, 3, 4, 5. Okay? So each landfill would get 125,000 tons of garbage. Okay, that's our number expanded and written out without scientific notation. Okay, make sure you have it down before we move to the next slide. All right, to go over some background information, we just did multiplication and division. We didn't actually do any addition or subtraction, but we will be doing that today. Multiplying in scientific notation, we multiply our numbers, we add the exponents. Okay, here's a little example right here for your reference if you need to see it. So if this was a number and this was a number, we would multiply those numbers together. And these are our exponents, we add them together. Okay? Or dividing in scientific notation, we do the same thing, but we divide the numbers and we subtract the exponents, right? So if these were our numbers, we would actually divide them and get an answer. And our exponents, we would subtract them and get an answer. And then the last one that we didn't practice in our examples was adding and subtracting. The first thing you need to do, make sure your numbers have the same exponent. Here you'll see that this is to the third, this is to the second. So they made both of these to the third just by, if they make this one number bigger, they make this one number smaller. You'll see they did that there. And then they can just add like regular, and they keep the same exponent that they had before. So this is our background review. Now we're going to get into a little bit of practice. Let's move on. Exercise 1. The speed of light is 300 million meters per second. The sun is approximately 1.5 times 10 to the 11th meters from Earth. How many seconds does it take for the sunlight to reach the Earth? All right, so we have this distance from the sun to the Earth, right? And it is 1.5 times 10 to the 11th meters. Okay, we want to figure out how fast light can get there, how many seconds it takes. It travels this fast in 1 second. So we're going to divide this number by this number, 300 million, and see how many times it fits into there. Because we're splitting it up, we're seeing how many times will this distance be covered. Because this is for 1 second, we want to figure out how many seconds it actually takes. Okay. First thing we need to do is write this 300 million in scientific notation. This becomes 3 times 10 to the 3, 6, 8. All right. From there, we are dividing. We have our total distance, which is 1.5 times 10 to the 11th. And we're dividing that by the speed of light, 3 times 10 to the 8th. All right, using what we just went over, I want you to go ahead and pause this video and solve this. And then once you have it solved, please come back and check it with me. All right, you should have paused the video and solved it on your own. When you do 1.5 divided by 3, you get 0.5. And when you do 11 take away 8, you get 3. All right. Now this is not correctly written in scientific notation. We would need to move this one space over, make it one space bigger. And when we do that, we make this one space smaller. We do the opposite. So 5 times 10 to the second. It's going to take that many seconds to get to Earth. We can also expand this and write it out. If we're moving this decimal 2 spaces to the right, 500 seconds to get to Earth. Okay, that is our final answer. Check it with mine. Make sure you have it all down. See where you might have made a mistake if you made a mistake, and then move to the next slide. It says the mass of the moon is about 7.3 times 10 to the 22nd kilograms. So it would take approximately 26 million moons to equal the mass of the sun. Determine the mass of the sun. So this is the mass of the moon, and if we did that 26 million times, it will equal the mass of the sun. We want to know what is the mass of the sun. So we are multiplying these because we're doing it that many times. First thing you need to do is write this number in scientific notation. Please do that real quick. Pause this video. All right, you should have had time to write that in scientific notation. This number is 2.6 times 10 to the 3, 6, 7, 7th power. And what we're going to be doing is we're going to be multiplying this number with this number. We have 7.3 times 10 to the 22nd, and we're multiplying it by this number. Go ahead and perform your multiplication, and then write your number in scientific notation, and then answer your word problem. Pause this video to do it, and then come back, press play to check your work. All right, 7.3 times 2.6, you should have got 18.98. The 22nd and the 7th, when we add those exponents up, we get times 10 to the 29th. This is not written in scientific notation. We need to move this one space back, make it one space smaller. And if we make that one space smaller, we make this one number bigger. So the final answer here is 1.898 times 10 to the 30th. And we just want to answer this. How many, determine the mass of the sun. The mass of the sun is 1.898 times 10 to the 30th, and this is in kilograms. That is our answer. We don't want to write this out and expand it as a real number because there are 30 spaces we would move, and that is just way too much. We're going to leave it in scientific notation. Okay, let's move on to our next exercise. Exercise 3 says the mass of the Earth is 5.9 times 10 to the 24th kilograms. The mass of Pluto is this huge number. I don't even know how to say this number. Compared to Pluto, how much greater is Earth's mass than Pluto's mass? So we have Earth and we have Pluto, and we want to figure out what is the difference. How much greater is Earth? If we're finding the difference between these, we're going to be subtracting. Okay? So the first thing we need to do is write this number in scientific notation. This is going to be 1.3 times 10 to the, make sure you count correctly, 3, 6, 9, 12, 15, 18, 21, 22. Okay? And we just keep this number right here. We have Earth's mass, which is a little bit bigger, 5.9 times 10 to the 24th. We want to figure out how much bigger it is, so we are subtracting. Now the first thing we need to do when we subtract is we need to make sure our exponents are the same. We can't subtract until these are the same. So we have a 24 and we have a 22. It's up to you what you want to do, if you want to make both of them 24 or both of them 22. I think I'm going to make them both 24. So this one's going to stay the same, 5.9 times 10 to the 24th. This one becomes a 24. So we went from 22 to 24. We added two numbers. So here we're going to move back 2 spaces. Okay? Make it 2 spaces smaller. So it's going to be right there. So it's going to be 0.013. You can put a 0 there if you want. Again, if we make our exponent bigger by 2 spaces, we make this number smaller by 2 spaces. Okay, now that we have the same exponent, we can go ahead and subtract. 5.9 minus 0.013. Let's do that real quick. 5.9 minus 0.013 is 5.887. Okay, and then we keep the exponent that we already had, times 10 to the 24th. We don't need to do anything else. All right, last step is to check and make sure this is in scientific notation, times 10 to the 24th. Our leading digit is between 1 and 10, so this is correct. But we do want to answer it. How much greater is Earth's mass than Pluto's mass? Earth's mass is 5.887 times 10 to the 24th. times, or what is it, kilograms? Kilograms bigger. That is our answer here. Okay. Make sure you have this one down. I know I just kind of went through this one on my own, but it's because we haven't seen subtraction since yesterday. Let's go ahead and move on. Exercise 4 says, using the information in exercises 2 and 3, find the mass of the Moon, Earth, and Pluto. So I'm just going to write these numbers down so you don't have to flip back. But the Moon, Earth, and Pluto, it was 7.3 times 10 to the 22nd. And we're combining that with 1.3 times 10 to the 22nd. And the last one, 5.9 times 10 to the 24th. I rounded some of these off a little bit. Okay? So we're going to add all these up. You can do this in steps if you want. I think I'm just going to add these two together first, and then I'll add the third one later on. And the reason why I'm adding those two together first is they already have the same exponent, right? They already have an exponent of 22, so I can just literally add these numbers up. So 7.3 plus 1.3 is 8.6. Okay? And then a half times 10 to the 22nd. And now I'm adding that with this last number here. All right? It's up to you if you want to make both of these a 22 or a 24. I think I'm going to change this one to a 24. So if this becomes 10 to the 24th, that's 2 spaces bigger. We need to make this 2 spaces smaller. So this is going to be 0.086. And we're adding this 5.9 times 10 to the 24th. Okay. I'll add my two numbers up. And what I get is, let's see, 5.9 plus 0.086. I get 5.986, and I keep my exponent 10 to the 24th. And this is already written in scientific notation, so this is correct. All I have to do is answer my question. The combined mass is 5.986 times 10 to the 24th kilograms. All right. Let's go ahead and move on once you have it down. All right, exercise 5, a little bit more confusing. It says, how many combined Moon, Earth, and Pluto masses, so our answer from the last one, are needed to equal the mass of the Sun, which was our answer to exercise 2. So our answer to exercise 2 was 898 times 10 to the 30th. So this is our Sun. And we're dividing that by our combined masses from our last answer, which was 986 times 10 to the 24th. Okay. Go ahead and solve this on your own. Pause this video and then come back and press play and check your work once you have it done. Alright, first thing you need to do is divide these numbers right here. When you divide this, you should get 0.3170 ... keeps going. I'm just going to round it to 0.32. Okay. And then you're subtracting these. 30 take away 24 is 6. And then we need to write our answer in scientific notation. This needs to get one space bigger, so we make this one number smaller. So our answer is 3.2 times 10 to the 5th. So it would take 3.2 times 10 to the 5th combine masses to equal the sun. That's how many times that number would fit in the sun. Kind of crazy. Very big planet or star. Okay, make sure you have it down before we move on. We are not going to do the problem set. Go ahead and skip that. Move to the next slide. All right, just to review our lesson, when we multiply in scientific notation, we multiply our numbers, we add the exponents, and then we always rewrite our answer in scientific notation correctly. When we divide the numbers, we subtract the exponents. Okay. The one that's a little bit trickier that we practiced a lot yesterday and didn't practice too much today is adding and subtracting. First, you have to make sure the numbers have the same exponent, and then you add numbers or subtract them, and you keep the exponent that you have. So that first step is probably the hardest, making sure they have the same exponent. Here, this is a 3, this is a 2. We wanted to make them both 3, so we made this a 3. That is one space bigger, so we made this one number smaller, or one space smaller. And then we just added these numbers like regular, and you kept 10 to the 3rd. Okay? Reference these examples if you need help on the exit ticket. Let's go ahead and go over what you're going to be doing on the exit ticket on the next slide. All right, here's your exit ticket for today. The questions are split up in Galileo to kind of scaffold it for you. It says the speed of light is 3 times 10 to the 8th meters per second. The sun is approximately this distance from Mars. How many seconds does it take for sunlight to reach Mars? So you're going to be doing some division. And then I've also added in some other questions on Galileo that aren't on here. They're kind of mystery questions, but it's just straight computation, not even word problems. Adding, subtracting, multiplying, and dividing. So please head over to Galileo and complete your exit ticket. When you're done, please do your reflection in Google Classroom and work on any missing or weekly work.